Autonomous vehicles, or AVs, have presented themselves as the future of transportation. At the same time, city plans are increasingly integrating shared spaces, which are low-speed environments that allow for different types of road users to coexist. These changes meet and create a new and important challenge. AVs must learn to drive through these shared spaces. What makes this task different from navigating through roadways or crossings is that human behavior is more sporadic and categorized by these complex social arrangements we see here. So imagine you're walking along Eastern Avenue and someone walks a little bit too close or cuts through your social group. This might be safe, but it's certainly awkward and uncomfortable. We know this, and if AVs want to also join shared spaces, they must exercise this same level of social politeness. Thus, the successful integration of AVs into these shared spaces is dependent on public acceptability and comfortability, which requires an adherence to social norms through an understanding of social arrangement. This problem forms the basis of this thesis. Now, currently, most AVs treat pedestrians like avoidable objects. This can lead to social spaces being impeded on. Human spatial behavior theories and sociology provide interesting categorizations of humans and their interactions with each other and their environment. For example, proxemics quantifies a human's personal space. Researchers in social robotics have attempted to integrate this when dealing with people and robot interactions during navigation. Perhaps these principles can be transitioned over to AVs. This thesis thus presents the social activity zone detection system, which attempts to detect complex social zones by leveraging theories from sociology and then uses this to help facilitate sociable navigation in shared spaces. The system is developed on the UCID campus dataset, collecting using the Australian Centre for Field Robotics Intelligent Transport System Autonomous Vehicle, and is one of the few pedestrian datasets that include shared spaces. The system has three fundamental tasks: pedestrian tracking, social space detection, and informed navigation. The first task of pedestrian tracking is premised on the finding from analyzing the dataset that in order to detect social activity, two cues are integral: a pedestrian's position and their pose. Thus, optimal fusion of LiDAR and RGB sensor data to track these cues is explored. For position, YOLO V4 and Deep Sort are used to track the bounding boxes that encapsulate the pedestrians in the image frame. The bounding boxes are then used to extract the pedestrian's respective point cloud section. DB-Scan and Ransack are employed to cluster the pedestrian. Now, semantic segmentation can be used to eliminate noise from the bounding box, and a comparison indicates that it improves accuracy. However, the increased computational expense reduces suitability. Taking the medium of the final cloud gives the pedestrian position that can be transformed to a world frame. Gaussian filter-based fitting is used to obtain the pedestrian's historical path. For pose, the top portion of a pedestrian's bounding box is passed to image to pose, a detector which estimates the road pitch and yaw of a pedestrian's head. Given that some detections can be missed, the pedestrian's path trajectory can be used to estimate pose as a backup. Through this, the system accurately tracks 85% of detected pedestrians who are up to 15 meters away from the vehicle. However, occlusions still reduce observability. This is an example of tracking for a moderately crowded scene. The top view of the world is shown on the right. A ROS visualization tool is also created to provide the 3D view of the pedestrian tracking shown on the bottom. The second task involves using the output of the tracking module in order to detect social zones. This thesis first fuses the proxemic and information processing zone from literature into a novel space called the dynamic personal zone, facilitating attentiveness to personal comfortability. This is an example of the detected zone for a single pedestrian. Now, to detect social groups, this thesis proposes an algorithm that assigns pedestrians into groups based on the overlap between their personal zones. The center of the interaction and distances between group members are used to quantify the social space called the social group zone. The system's ability to detect personal and social zones means that the AV is given social awareness of the surrounding environment. The system is tested on diverse scenes of varied difficulty. The world view plot shows the zones for each pedestrian, while the green circles are the group detections. Not only does the system consistently track the personal zones of pedestrians, but it accurately detects groupings of varied size, formation, and distance from the vehicle. These detections are only useful if they can be used to inform the autonomous vehicle's navigation. A map conversion tool is developed that creates a cost map for both the personal and social zones. Adding these layers to the navigation stack's existing layers reduces the likelihood that social activity will be impeded on and allows the vehicle to obtain a sense of social attentiveness. This thesis proposed a method for optimally processing and fusing RGB and LiDAR data to obtain position and pose. This thesis also introduced two zones to help detect and quantify social behaviors and groups in shared spaces. Finally, this thesis proposed how social awareness can be embedded into a vehicle's navigation system. The next step is to directly test the system on the Australian Centre for Field Robotics ITS vehicle. The time complexity of the detection algorithms confirms the feasibility of live testing. Future work also includes using the developed algorithms to label zones in a dataset and then train a neural network that can perform these detections. Studying whether the social zones are still accurate in the current era of social distancing might provide interesting insights. Overall, the results of this thesis indicate that optimally fusing sensor data to detect social activity can enable the vehicle to navigate around shared spaces in a manner that conforms with social norms and thus improves the likelihood of AVs being accepted in shared spaces.